Hello and welcome to the 8th episode of the second season of the Young Researchers Forum on Detonation. Today's presenter is going to be Sandeep Dammati. Sandeep Dammati obtained his bachelor's and master's degree in aerospace engineering from the Indian Institute of Technology in Kharagpur. During his stay, he was awarded an ARDB fellowship and worked on computational investigations of flapping winged aerodynamics for his thesis. After graduation, he worked briefly as a software engineer at Altair Engineering in Bangalore, where he was developing computational tools for their HyperWorks CFD program. He's currently a PhD student in the Department of Aerospace Engineering at Texas A&M University, where he's working on the development of massively parallel platforms for direct numerical simulations of multi-phase hydrocarbon combustion. Mr. Dammati is also working as a research specialist at the University of Connecticut, where he is right now, in Storrs, where he's studying the propagation limits of gas phase detonations in light and heavy hydrocarbons in narrow channels. His research interests include high-performance computing, high-speed compressible turbulence, and multi-phase flames and detonations. This talk is being recorded and it will be edited and posted on our website once the speaker approves a final version. I'll post the link to the website in the chat. This website, you can find previous talks and information on upcoming talks. If you have any questions during the presentation, I encourage you to ask them in the chat or wait till the end of the presentation where we'll have a discussion. So I'd like to welcome Sandeep Dammati. The platform is yours.
Okay. Yeah. Good afternoon, everyone. My name is Sandeep. Thank you for the introduction. So I'm a PhD student in the Department of Aerospace Engineering at Texas A&M University under Dr. Alexei Podolenko. So today, we're going to start. So we'll discuss some of the work we have been doing on numerical investigation of on the accuracy of particle image velocimetry technique in high-speed flows. So this work has been done in collaboration with Dr. Yoram Kozak from Tel Aviv University and Cal, Jonathan, and Dr. Karim Ahmad from University of Central Florida. So let's begin. Motivation. So a wide range of natural systems involve, such as type 1 supernova explosions and explosions in fuel storage units often involve detonative combustion. In recent years, there have been an increased interest in developing propulsion systems based off of detonation combustion, such as rotating detonation engines and oblique detonation wave engines for hypersonic flow application, hypersonic combustion applications as an alternative to the traditional scramjet engines. Now, in order for proper design and operation of these systems, require in-depth analysis of the detonation structure as well as its dynamics, which is often characterized by highly unstable cellular structures like the one shown on the right-hand side, which is a soot foil from methane oxygen mixture. And in addition to this, we also have what are known as triple point collisions on the detonation front, which often lead to extreme pressures and temperatures, like the one shown on the right. Here is a joint PDF that shows the pressure versus temperature extracted from Lagrangian trajectories in a hydrogen air detonation. As you can see, the pressure can get really high. Now all this complex structure and all of these extreme high temperature and pressure makes the characterization of detonations very challenging, both experimentally as well as numerically. Now, if one considers all the experimental techniques that are out there to characterize a complex flow, they broadly classify into two categories. On one hand, you have these advanced velocimetry techniques known as molecular tagging velocimetry, like KTV, which is krypton tagging velocimetry, FLEET. So these techniques involve complex optical setups or seeding the flow with molecular species. Though these methods show good promise for detonations, these still require advances in terms of timing, noise level, and tracking accuracy. So in recent years, this has led many of the experimentalists to use a more canonical velocimetry approach, such as particle image velocimetry or PIV, to characterize high-speed flows. Now, PIV is a particle seeding approach that allows one to do instantaneous flow field characterization. So However, the way you do a PIV experiment is you take the flow field of your interest and you seed the flow field with very tiny particles, and you evolve the flow. Then you shine a laser and you illuminate a plane in the flow field, and you capture images of the motion of the particles in that plane at a certain imaging frequency. Now you try to reconstruct the velocity information in that plane by tracking movements of the particles in the captured image pair. Now, in order for PIV to work, the following conditions have to be met. First, you seed the flow field with particles, and the expectation is that these particles don't affect the flow field in any way. But the question is PIV really non-intrusive for these high-speed flows? Secondly, in order to capture all the relevant flow dynamics, the particles have to sample the flow field properly. Having said that, when you put inertial particles in a turbulent flow, they undergo what is known as particle clustering. To show this, on the right-hand side is a movie of showing inertial particles in a homogeneous isotropic turbulent flow. And as you can see, the particles tend to aggregate into these regions known as clusters, and they segregate to form these regions of void. So this leads to an irregular sampling of the flow field. So one can ask the question, do these particles sample the flow field uniformly in these high-speed flows? And thirdly, and most importantly, PIV heavily relies on the ability of the seed particles to follow the flow field accurately. But in reality, this inherently limits the accuracy of PIV, because in reality, these particles have mass, and mass leads to inertia, and inertia leads to lag in particle response time to flow field changes. And this particle lag in response time becomes more pronounced with high velocity gradients like shocks. To demonstrate this, on the right-hand side, I took a periodic domain in 2D, and I seeded the entire domain with both massive and massless particles, which are initially co-located. And then when I send a blast wave through this, you can see that the massive particles and the massless particles deviate from each other very quickly. So one can ask the question, what is the accuracy of the seed particle trajectories compared to the actual Lagrangian trajectories? Then finally, what is the accuracy of the PIV reconstructed field in comparison with the actual velocity field? Now, before one applies PIV or uses PIV technique to characterize any kind of complex flow, it is important to have answers to these questions so that you get an idea of what kind of accuracy can you expect in your results. Since finding the accuracy of PIV can be really hard in an experimental setup, we use numerical PIV to address some of these questions that I listed above, and to see if we can learn anything from numerical PIV that would help the experimentalists. Now, before I get into numerical PIV, I'll briefly talk about the code, the solver that we are going to use in this study. So the solver is Athena RFX multiphase, which is a multiphase extension of the reacting flow solver Athena RFX. Athena RFX is a very mature, fully compressible reacting flow solver. It is conservative up to machine precision, and it has been in the past, over the decade, it has been used to study a wide variety of flow field turbulent combustion problems, such as deflagration to detonation transition on the right, and several turbulent combustion cases. In addition, the code is also able to do both heterogeneous solid particle combustion as well as liquid droplet spray combustion. You can see on the left bottom side is a spray in a swirl combustor, and in the middle is a dodecane air multi-phase jet fuel spray in the same swirl combustor. We use an Eulerian Lagrangian formulation. So the gas field is simulated in an Eulerian grid, and the particles are tracked using a Lagrangian formulation. And both gas and the particles are two-way coupled. That is, the particles can exchange both momentum and energy with the gas, and vice versa. We use a more state-of-the-art Reynolds number and Mach number dependent drag law. And the code is massively parallel with a weak scaling greater than up to 90% on 100,000 codes. Now, the strategy of how we do numerical PIV. So in an ideal case, you want to carry out the numerical PIV study in a 3D detonation. But in general, 3D gas phase detonations are by themselves very computationally costly. On top of that, if you want to make it a multi-phase 3D detonation with Lagrangian particles, it almost becomes computationally prohibitive. So we follow the policy of divide and conquer. So what we do is we first perform numerical PIV in a 2D detonation and see what is the accuracy of PIV in a 2D detonation. 2D detonation, 2D planar detonation in some sense captures more or less the main features of a three-dimensional detonation, if not for all the features. So in some sense, it is okay to simulate a 2D detonations, check the accuracy of PIV. And secondly, for the downstream location of the detonation, which has more or less reached a chemical equilibrium and where there are no shocks present, and the flow is more or less turbulent, we carry out numerical PIV in a 3D turbulent flow to see what is the accuracy of PIV in downstream of a detonation. So first, we look at numerical PIV in 2D detonations. So we carry out the numerical PIV in a 2D channel with hydrogen air mixture at atmospheric conditions. So here is the 2D channel on the right. So the upstream of the upstream is moving at CJ detonation velocity. So the problem is being solved in the shock frame of reference. So we initialize the solution with a perturbed ZND solution, which collapses and creates local blasts, as you can see here, and that initiates the transverse motion required for a multidimensional detonation. So the walls here, the top and bottom walls are adiabatic slip, so there is no loss. And we use outflow boundary conditions at the left and the right boundary. We use ideal gas equation of state and single step chemistry calibrated by Brian Taylor. Now, once we see the detonation more or less reaches a steady state, we seed massive particles from the left-hand side of the domain. These massive particles are monodispersed aluminum oxide particles, which represent the PIV particles in an experiment. And once each massive particle reaches the shock front, we place a Lagrangian tracer particle on top of it to track the accuracy of the massive particle as it traverses through the detonation structure. We experimented with two particle sizes, 200 nanometers and 50 nanometers. We seeded about 500,000 particles. We also carried out complementary single phase runs without any particles to quantify the effect of the seed particles on the gas phase. Okay, first let's try to see if PIV is non-intrusive for these detonations. So in order to quantify this, first we look at the time average propagation velocity of the detonation front for all the three cases. As you can see on the right, the velocity more or less remains the same between the single phase case and both the multi-phase cases. So we observe no significant effect in both the multi-phase cases. Next, we look at what is the effect on the thermodynamic state of the detonation. So for that, we plot the difference in the pressure specific volume joint PDF between the single phase case and the 200 nanometer case. As you can see, the difference in probability is less than 10 to the power minus 3, indicating that there is very little effect by the seed particles. Next, we look at the transverse velocity field. So on the right is the PDF that shows the transverse velocity, normalized transverse velocity field, normalized using the CJ velocity for the single phase case and both the multi-phase case. As you can see, the PDFs fall on top of each other, indicating there is no significant effect. Finally, we look at the detonation structure and see if there is any change in the detonation front structure. And as you can see, the detonation structure more or less remains intact without any noticeable changes. So in conclusion, we conclude that there is negligible effect of PIV particles on the detonation, which is good for PIV. These results also suggest that the detonation cellular structure is not affected, but this analysis will be presented in a separate paper. The next question is, do these particles sample the flow field properly? As I mentioned before, when you put inertial particles in a turbulent flow field, they tend to cluster, and this can lead to non-uniform sampling. We observe this clustering phenomenon even in our simulations. So if you can, here I'm showing the synthetic PIV images for 200 nanometer massive particles case, 50 nanometers case, and the massless case. As you can see, there is clustering and voids in case of both the massive particles. Having said that, it is important to note that our simulations here are two-dimensional. So this effect is more exaggerated in 2D as compared to a 3D case, because in 2D, turbulence follows an inverse cascade, which implies that the large-scale motions are enhanced and the small-scale motions are attenuated. Nevertheless, we try to quantify what is the amount of clustering in our simulations. So the first technique that we'll use to quantify clustering is known as box counting method. this is a very simple method in which you take the domain and you divide it into small boxes, and you basically count how many boxes, how many particles do you have in each box. Here we take the size of the box to be the PIV interrogation window, which is 0.32 millimeter. And in an ideal case, if the particles are uniformly randomly distributed, the PDF should follow a Poisson distribution. So on the left is a PDF of how many particles do I have per each box. And as you can see, the massive particles show significant deviation from the Poisson distribution, whereas the massive particles are closer to the Poisson distribution. This indicates that there is significant amount of clustering in case of massive particles. Now, since box counting method involves an explicitly specified length scale, which is the side length of the box, it is not always ideal to use that technique to quantify clustering. So people have proposed Knighttessellations to be the alternative technique. So in Knighttessellations, you basically divide the domain into Voronoi cells, so associated with each particle. So a Voronoi cell is basically locus of all the points in the space that are closer to a given particle compared to any other particle in the domain. So in some sense, Voronoi tessellation will tell you the local concentration of a particle. So if you can see this image, in regions where the particles are far away from each other, the cells are larger, and regions where the particles are closer to each other, the cells are small. So if one constructs a PDF of the normalized Voronoi cell area, normalized by the mean value, it should also follow a Poisson distribution if the sampling is uniform. So on the right is a PDF that shows the normalized Voronoi cell area. The green line is the Poisson distribution. And as you can see, the massless particles, which are the red square dots, accurately follow the Poisson distribution, indicating that there is no significant clustering in case of massless particles. But if you consider the massive particles, you see significant amount of deviation from the Poisson distribution. So we quantify the deviation in terms of the standard deviation in this PDF. As you can see, the standard deviation for a 2D Poisson distribution is 0.53. And for the massless particles, we find it to be 0.54, indicating that it closely follows the Poisson distribution. But for the 200 nanometer case, the standard deviation is 1.64. And for the 50 nanometer case, it's 0.78. So this indicates that in case of both massive particles, there is significant clustering. But in comparison, 50 nanometers particles sample the flow field better than 200 nanometer particles. Now coming to the third question, what is the accuracy of the seed particle trajectories? Now PIV heavily relies on the ability of these seed particles to track the actual flow path lines. But if you compare the initially co-located massive particles and the massless particles, you can see that from the movie on the right that the massive particles rapidly diverge from the massless particles during shock crossing. Now, having said that, PIV works based on a pair of images. So what actually PIV cares is what is the accuracy of the massive particle trajectory as you advect it from time t1 to t2, rather than the entire trajectory, just the image pair. So in order to quantify this error, we take the massive particles at t1 and we reseed them again with massless particles on the top, and we evolve them from t1 to t2. And the delta t is the imaging frequency, basically. So if you look at what is the error within an image pair, so here is a PDF showing the difference in the position of massive particles in comparison with the massless particles within an image pair, and the error is normalized with the PIV interrogation window. You can see that the error is largest in case of 20 nanometer case near the shock, and it is less in case of 50 nanometer particles. As you go away from the shock, the error seems to decrease. But in both the cases, the error is within one PIV interrogation window. Now we finally come to the PIV reconstruction. So in order to perform PIV reconstruction, we construct a synthetic PIV, we construct synthetic PIV images of the flow field for all the three cases. Here, the time step between each image pair is 0.1 microseconds, which corresponds to an imaging frequency of 10 megahertz. The intensity profile within each PIV image is approximated using a Gaussian. Please note that here the massless particle field is the best case scenario for PIV reconstruction because the massless particles don't suffer from particle clustering and they follow the flow path lines accurately. Now, here are some instantaneous velocity fields from PIV reconstruction. So at the bottom, you have the actual velocity field from the simulation. This is streamwise velocity, and this is the transverse velocity. On the top, you have PIV reconstructed velocity fields from the massless particle field. And above that, you have the massive particles 200 nanometer case. As you can see, this shows the ability of PIV to reconstruct the bulk features within the flow field. There is noticeable correlation in the streamwise direction between the actual velocity field and the reconstructed velocity fields. We, in relative sense, we observe better reconstruction in case of massless particles as compared to the massive particles. Now, before we quantify the error in the reconstructed velocity fields, we first look at the uncertainties associated with this PIV reconstruction. So the uncertainties are introduced by imaging, the cross-correlation procedure, which basically tracks the particles between two image pairs to reconstruct the velocity field and also the particle response time. So on the right, I'm showing the uncertainty in the PIV reconstruction. And here the uncertainty in both streamwise and transverse direction. And the uncertainty is normalized with the local velocity field. As you can see, the uncertainty is very low in case of massless particles because there are no voids or clusters. And there is no lag in particle response time. But in case of massive particles, you see less uncertainty in case of 50 nanometers as compared to the 200 nanometer case. The reason is that there are less voids, or the voids are smaller in case of, or less particle clustering is present in 50 nanometer case as compared to 200 nanometer case. And also the 50 nanometer particles have a better particle response time in comparison with the 200 nanometer particles. And if you compare the streamwise and the transverse direction, you see that there is a lot of uncertainty relatively in case of the transverse motion as compared to the streamwise motion, because the bulk of the flow is moving in the streamwise direction. Now, finally, we compute the error in the reconstructed velocity fields. So on the right, I'm showing the contours of the error in the velocity field for both streamwise and the transverse direction. Here, the error is normalized with the local velocity of the local velocity from the true velocity field. As you can see, the errors are larger near the detonation front for both massive and massless particles. And as you go downstream of the detonation, you see the errors become less and less. The same can be seen from the PDF on the left. Now, to investigate this further, what we did is we took a centerline cut through these reconstructed profiles, and we compared them with from the centerline cut from the DNS or the simulations. So the plot on the right shows the streamwise velocity along the centerline cut for both from the numerical simulation, which is shown by this blue line, and for the 50 nanometer from the reconstructed velocity field from the 50 nanometer case, and for the massless particle case. And here the dashed line is the CJ velocity. What you see is that the massless particles are able to capture the jump in the detonation across the detonation front, whereas you see a significant velocity deficit in case of the massive particle reconstructed velocity field. And this deficit is around 25 to 30%. But as you go downstream, you see that PIV more or less captures the features present within the flow field, missing only the local fluctuations. So in conclusion, PIV captures the bulk flow features in the streamwise direction. However, its accuracy is inadequate to capture any kind of local fluctuation or any kind of transverse motion. So in conclusion, we say that, so we performed the first detailed numerical study to quantify the accuracy of PIV technique in highly compressible reacting flows. We saw that there is no significant effect by the seed particles on the detonation, which is good for PIV. We saw that there is irregular sampling of the flow field by the massive particles. Massless particles seem to sample the flow field properly, whereas the massless particles show significant particle clustering. In comparison, the 50 nanometer particles sample the flow field better as compared to the 200 nanometers particles. Finally, we saw that the massive particles quickly diverge from the actual flow path lines during shock crossing. Finally, when we compared the synthetic PIV reconstructed fields, we saw that there is significant velocity deficit in case of massive particles reconstructed field, as the massless particles seem to capture the jump in the velocity across the detonation. We saw that PIV captures the bulk flow features within the flow field in the streamwise direction. However, its accuracy is inadequate to capture local flow fluctuations. So the take-home message from this 2D detonation study is that if you are using PIV to, let's say, study rotating detonation engines, you have to be careful. You might be able to capture some kind of bulk flow features within the system. However, if you are looking for any kind of localized fluctuation or localized statistics, PIV might not be your best bet. So now we move on to carrying out the numerical PIV in 3D homogeneous isotropic turbulence. That is the downstream of the detonation. So we carry out this study in a 3D periodic box filled with methane air mixture at atmospheric conditions. The domain is 0.45 millimeters, and we accurately resolve the Kolmogorov scale with 2 cells per Kolmogorov scale. So the turbulence conditions that we are looking at correspond to a Taylor Reynolds number of 87, which is roughly the Reynolds number of 5,000, and the turbulent Mach number is 0.05. So these conditions that we are simulating are representative of unburned reactants side of a turbulent premixed methane air mixture at Karlovitz 200. So it is a pretty fast plane, though subsonic, it is high speed. So this is how we carry out PIV in 3D homogeneous isotropic turbulence. We take the domain and we initially seed the domain with 300 nanometer aluminum oxide particles, which represent the PIV particles typically used in a turbulent flame experiment. We initially evolved these particles for 2 eddy turnover times so that the turbulence is evolved in the domain. And after 2 eddy turnover times, at the location of each massive particle, we place a massless Lagrangian particle to track its accuracy. And we evolve the accuracy of its trajectory, and we evolve the domain for another 2 eddy turnover times, during which we perform the synthetic PIV reconstruction. So we seeded about 50 million particles in this simulation. So it's a large simulation. And we also carry out complementary single phase simulation without any particles to quantify the effect on the gas phase. So in comparison with the previous detonation study, here the turbulent Mach number is low, 0.05, which makes it a weakly compressible flow. The reason we chose this is to avoid any kind of shocks or shocklets, to simplify the problem and to see if in the absence of shocks, can PIV do it better. Also here, the flow is 3-dimensional as compared to the 2D detonation study. So the turbulence is more realistic here. And the particles have to go through the entire turbulent cascade of eddies, of large scale eddies to the small scale eddies. So first, we try to quantify what is the effect of these particles on the gas phase. So first, we look at the time average kinetic energy spectrum, which is shown in panel A here. So the blue line is from the single phase case, and the red line is from the multi-phase case. You can see that in case of multi-phase, you see that there is reduction in kinetic energy at the large scales, and there is an enhancement of kinetic energy at the small scales. So the reason for this is the gas around the particles have to do work to move the particles around. So the particles extract some energy from the gas itself, which leads to reduction in net kinetic energy in the gas. So here, basically, the particles extract energy from the large scale motions of the gas, and they try to move around. And while they move around, they seem to impart some part of this extracted kinetic energy back to the small scale motions in the gas. So that's why you see an enhancement of kinetic energy for the multi-phase case at the small scales. So we also looked at the URMS velocity between the single phase case and the multi-phase case, and we see a reduction of velocity deficit of 8.5%. And this a reduction in gas velocity basically is due to the fact that the gas had to do work or impart some velocity to the surrounding particles. So next we look at velocity statistics shown in panel B. The black line is the Gaussian distribution, and you can see between the single phase and the multi-phase case, they more or less follow the Gaussian statistics. However, if you look at velocity gradient statistics like entropy and pseudo dissipation rate, we see that there is a 30% reduction in the mean entropy and pseudo dissipation rate. And this reduction that we observe is consistent with previous studies in particle-laden flows at similar conditions. So in conclusion, this critically means that PIV may not be truly non-intrusive in these high-speed turbulent flow regimes. Next, we look at how well do these particles sample the flow field. Here I'm showing synthetic PIV images for the massive particles and the massless particles. As you can see, there is significant clustering of these white regions, and these black regions correspond to voids. So on the other hand, you can see that the massless particles are more or less uniformly distributed. So we'll try to quantify what is the amount of particle clustering in these 3D simulations as well. The first technique is the box counting technique, where you take the 3D domain and you divide it into boxes, and you basically count how many particles do I have in each box. So here we also take the PIV interrogation window size as the size of the box, which is 36 micron. And in an ideal case, the PDF should also follow a Poisson distribution. So on the left is a PDF of how many number of particles do I have per each box. As you can see, the blue line here is the Poisson distribution. As you can see, the massless particles follow the Poisson distribution very accurately, whereas you see a wide distribution in case of massive particles. So it means that in case of massive particles, there are some boxes where there are no particles at all, and there are boxes where you have very large number of particles. So this leads to very irregular sampling of the flow field. Now, as I mentioned earlier, box counting method is not always ideal to look at particle clustering. So we will also look at Knighttessellations. Here we carry out Knighttessellations based on the 2D images, PIV images, because traditionally that's how experimentally people have also looked at clustering in PIV experiments. So just to recap, Warnoy cells are basically associated with each particles are basically the locus of all the points that are closer to a given particle as compared to any other particle in the domain. So if the cells are large, it means that the particles are distributed widely. And if the cells are closer or small, it means that there's a particle clustering. Now, if you construct a PDF of the normalized Warnoy cell area, it should also follow a Poisson distribution, that is this blue line. You can see that in case of massless particles, it exactly follows the Poisson distribution, again indicating that there is no clustering in case of massless particles. But in case of massive particles, you see there is a wide distribution. Now, this massive particle PDF intersects the Poisson distribution at two locations. The locations to the left of this line, this dashed line, are said to belong to clusters, and the Warnoy cells that are on the right-hand side of this right dotted line are said to belong to voids because they have larger areas. Now, to quantify this, we look at the standard deviation in this PDF. Again, the Poisson distribution, the standard deviation is 0.53. For the massless particle case, we also found that it is the standard deviation is 0.53, indicating that it closely follows the Poisson distribution. Whereas for the massive particles case, it's almost 3 times the standard deviation in the Poisson distribution. Therefore, we observe highly irregular sampling of the flow field. Now, like I said before, PIV heavily relies on the accuracy of the seed particle trajectories to follow in following the flow path lines. So first, what we do is we compare the accuracy of the seed particles with the initially co-located massless particles. Here is a PDF that shows the error in the trajectory normalized with the PIV interrogation window size. And we compare the trajectories at different imaging frequencies or different time intervals to see what is the best imaging frequency for PIV so that the error in the trajectory will be small. So we went from 500 kilohertz, which corresponds to 2 microseconds, all the way to 10 kilohertz, which is like 2000 microseconds. As you can see, the blue line, which corresponds to the 500 kilohertz case, the error is within one PIV interrogation window box size. And as you lower the PIV, the imaging frequency, you see that the error shifts to the right. That is, error gets larger and larger than the PIV interrogation window size. So we conclude that any imaging frequency less than 500 kilohertz can lead to increase in seed particle trajectory error. Further, we also look at what is the difference between the velocities of the seed particles with the local gas velocity, because this difference is important, because this difference is what it leads to particle lag, also what causes the trajectories to diverge. So here I'm showing a PDF of particle velocity minus the local gas velocity divided by the local gas velocity. So for the x velocity as well as the velocity magnitude, what you see is that there is significant difference in between the particle velocity as well as the gas velocity. And this comes from the fact that the particles have mass, which leads to delay in particle response time to flow field changes. We observed that around 52% of particles show less than 10% difference in velocity as compared to the local gas velocity, and the rest show more than 10% velocity deviation. Okay. Now, before we perform the synthetic PIV reconstruction on this 3D turbulent flow field, we wanted to first do some kind of validation study on the way how we generate the PIV images and how we perform the synthetic PIV diagnostics. So for this purpose, we first simulate and apply PIV diagnostics to a simple 2D Taylor-Green vortex problem. So a Taylor-Green vortex, as I'm sure many of you know, is a canonical unsteady 2D fluid problem with a known velocity fields. So we know what the solution looks like. So we can use that as a comparison with our PIV reconstructed velocity fields to see if our post-processing PIV techniques are accurate. So here is a typical Taylor-Green vortex, which shows a pair of rotating clockwise and anti-clockwise rotating vortices. And so we've performed the synthetic PIV in this Taylor-Green vortex at 2 meters per second and 20 meters per second. And here are the synthetic PIV images of the massive particles in a 2D Taylor-Green vortex. Now, if you look at here, I'm showing the Taylor-Green vortex fields from the DNS, that is the numerical simulation for the 2 meters per second case and the 20 meters per second case. In the middle are the PIV reconstructed velocity fields at the top and the bottom. And on the right is the error in the reconstructed velocity field normalized with the DNS true velocity field as a percentage. So what you see is that PIV is able to qualitatively reconstruct the velocity field. PIV captures the gas velocity with very good accuracy within each vortex box. So if you look at here, the error is less than 5%. Even this, the 20 meters per second case within each box, PIV more or less captures the local gas velocity accurately. However, the errors begin to increase as you move away from the center of each box towards the regions where you have a strong shearing motion of the gas. Like you can see here, the errors are largest here. Now, if one investigates what's the reason for this, so essentially here, the gas velocity in these regions of high error is essentially 0. However, when you try to perform PIV and you put an interrogation window there and you try to correlate the motion of particles in that PIV interrogation window, what happens is that the PIV cross-correlation algorithm considers all the motion of the particles within each interrogation box. So when you average, and it gives out only one averaged velocity vector per PIV interrogation window. So when you account for all the particle motion inside the PIV box, and you try to get an average velocity out of it, this average velocity gives a higher velocity than the actual gas velocity here. So that leads to increase in errors in regions where you have shearing motion of the gas. Now that we have validated our particle generation and synthetic PIV reconstruction, we'll now proceed to synthetic PIV reconstruction in the 3D case. So this is how we extract the images for the 3D turbulent case. So here, the black box shows our 3D periodic domain, and the green sheet here corresponds to the laser sheet used in a PIV experiment, and the black dots are the particles. As you can see, the laser sheet in principle is thick. It's not a very thin sheet. So there is a finite thickness to the laser sheet. So then we isolate the particles that are present within this laser 3D sheet, and then we suppress them to one single plane to get a 2D PIV image. Here on the left, I show how we do it. So here the entire domain collapses. You have this 3D PIV slab or the PIV laser sheet thickness. And these are the particles inside the PIV laser sheet. And then we suppress them to a single plane to get a PIV image as shown on the right. So we construct the synthetic PIV images for both massive particles and the massless particles. Here, the laser sheet thickness is 0.5 millimeter, which is typically what is used in turbulent flame experiments, PIV experiments. And the time step between each image pair is 2 microseconds, which corresponds to an imaging frequency of 500 kilohertz. Again, the intensity profile is approximated using a Gaussian in these PIV images. And the massless particle field, again, is the best case scenario for PIV reconstruction here. Here are some instantaneous velocity fields. So on the left is the DNS, the true velocity field along the x direction from the DNS. On the center is the PIV reconstructed velocity field using the massive particles. And on the right is from the massless particles. You can see that PIV captures the bulk features within the flow field. And again, we observe better reconstruction in case of massless particles as compared to the massive particles. Now, in order to determine what are the optimal set of parameters that are best for synthetic PIV reconstruction, we vary 3 items. The first item is the particle seeding density. So SD1 is the actual particle seeding density that we used in the simulation. Basically, it is the interdroplet spacing or the number of particles you have within that PIV slab. We keep reducing the particle seeding density from SD1 to SD3, which changes the number of particles located inside the PIV laser sheet to see which seeding density gives the best result for synthetic PIV reconstruction. At the bottom here, I'm showing the synthetic PIV images for different seeding densities. So SD1 is the highest seeding density that we used, and then we reduce the interdroplet space. We increase the interdroplet spacing by a factor of 2. Then we get SD2, which reduces the number of particles in the PIV slab, and then we double it again, which significantly reduces the particles inside the PIV slab. In similar way, one can also vary the thickness of the laser sheet. So typically, laser sheet is 500 micron, close to 500 micron. So we try to reduce the laser sheet thickness. We made it smaller and smaller to see if that can improve the accuracy of PIV reconstruction. And for each case, we also tried 3 different PIV interrogation window sizes to see what is the best interrogation window to get more accurate result. So if you play with these 3 parameters, this results in a total of 27 PIV reconstructed velocity fields for comparison. Now, so first, before we do a point-wise comparison of the velocity fields, we first look at some kind of global quantity to see if PIV can capture the global quantities properly. For that, we chose the RMS velocity. So URMS is basically an important global quantity in homogeneous isotropic turbulent flows, which is directly related to the equilibrium kinetic energy and also to the integral velocity scale in the flow. So here I'm showing in each panel, basically I'm comparing the URMS of the DNS, which is this dashed line, with the URMS from the PIV reconstructed fields for all the 27 cases. So what you see is that in most cases, the velocity, the URMS from the reconstructed velocity field is somewhere around 13 meters per second, while the URMS in the DNS is around 16.38 meters per second. So we observe an error of about 20%. However, there is one case where it seems to capture the PIV. The PIV seems to capture the URMS in the DNS, but it can be just luck. So we'll further investigate this by doing a point-wise comparison of the velocity fields. Now, so there is always this question of what to compare with, because if you see, the 3D laser sheet in principle is three-dimensional. It is not a plane of illumination, rather it's a laser sheet of finite thickness. So if one considers, so on the right, what I'm showing is the X velocity field at different locations inside the PIV slab from the DNS. So basically what you see as you go in the normal direction across the PIV slab is that the velocity field changes very significantly. So one can ask the question, so which exact XY plane velocity within the PIV laser sheet does the PIV reconstructed velocity field actually represent? Does it represent the center plane velocity within the laser sheet, or some kind of other plane that is located back and forth, or some kind of averaged velocity field within the laser sheet? So this is an important question. So in order to address this, what we'll do is we'll compare the 27 reconstructed velocity fields with different planes within the PIV laser sheet from the DNS. Further, this question often comes up in PIV experiments. That is, does the PIV reconstructed velocity field actually represent the velocity field, the true velocity field, such as the velocity field from the DNS, or some kind of filtered velocity field? So in order to address this question, what we did is we took the actual velocity field, which is shown at the top here from the DNS, and we filtered it using different PIV window sizes. So we go from 24 cross 24 pixels all the way to 128 cross 128 pixels. So basically we are increasing the filter width. And as you can see, as we increase the filter width, the small scale motions are lost, which is what filtering does typically. So in addition to comparison with the DNS velocity field at every XY plane, we'll also compare with the filtered velocity when we perform this point-wise comparison. So yeah, finally we come to the point-wise comparison of the velocity fields. So we'll just compare the X velocity field for now, since the flow is isotropic, so the direction doesn't matter. So we'll compare the mean normalized error here in X velocity, which we define it as epsilon, which is the velocity field from the PIV minus our reference velocity field, which can be either from the DNS or the filtered velocity field, normalized by the local velocity reference velocity. And we take a mean of that at all the points within the PIV reconstructed field. So if you compute epsilon, this is how it looks. Sorry. Okay, so I'll explain what this plot is. So here is this mean normalized error for seeding density 1. So if you consider this top, so as I go from bottom to top to bottom, basically I'm increasing the laser sheet thickness. And within each box, I basically compare what is epsilon at different XY plane locations within the PIV laser sheet. And at each location, I compare different interrogation window sizes for using both the DNS velocity field as well as the filtered velocity field. So what you see is that nothing seems to matter. The errors are huge. So epsilon of 2 means that there is 200% mean normalized error in the reconstructed velocity field. The two things that you can take away is as you come to the center of the laser sheet, the error seems to decrease in almost all the cases. And the errors seem to be minimal relatively in case of filtered velocity fields, which are these dashed lines, as compared to the solid lines for each case. We see the same result for the seeding density too. As you decrease the seeding density, in some sense, the number of particles decreases. So in some sense, you're losing the velocity information and the errors become huge. And as D3, the errors are very large. So since the point-wise comparison showed us that the errors are huge, so we thought, okay, can PIV capture any kind of statistics instead of maybe going for the instantaneous or the point-wise comparison of velocity fields might be too far-fetched for PIV. So we wanted to see if you can get some statistics out of the reconstructed velocity field. So for that, here I'm showing PDFs of the velocity field, normalized entropy, and normalized pseudo-dissipation rate. So you see that the velocity statistics are more or less Gaussian, even in the PIV reconstructed field for both massive and massless particles. But you see for velocity gradient statistics, such as entropy and pseudo-dissipation rate, there is significant deviation. And this deviation comes from the fact that you're not accurately resolving the flow field. Now, so let's try to identify what are the sources of error. So we identify four sources of errors. The first two, in my view, can be tackled, and the third and the fourth are in some sense inherent to the PIV technique itself. So the first error comes from the fact that the particles don't sample the flow field properly. They have irregular sampling, which means that you're not capturing all the flow field dynamics, which shows up as a huge error when you reconstruct the velocity field. The second error comes from the fact that there's a lag in particle response to flow field changes, which causes the particles to diverge from the flow field trajectories. Also, the particles don't relax to the local gas velocity, which gives a false velocity information to PIV diagnostics. So in my view, these two errors can be reduced by decreasing the particle size. So if you decrease particle size, keeping everything else constant, you basically decrease the Stokes number of the particle. And as the Stokes number goes low or begins to reduce, particles behave more and more like massless Lagrangian tracer particles. So this particle lag becomes smaller and smaller as you decrease the particle sizes. Also, it is a well-established fact or well-accepted fact in the particle-laden flow community that as you reduce the Stokes number of the particles tendency to cluster and create these voids become smaller and smaller. So in some sense, going to a smaller particle size can help with these two errors. But the next two errors are inherent to PIV technique itself, and they come from the issue of PIV resolution. So the third error, to demonstrate the third error, I have plotted the turbulent kinetic energy spectrum. This is energy in each wave number versus a wave number. And the blue line is the spectrum. And on top of it, I plotted the wave number corresponding to different spatial scales. Here, in terms of PIV, the spatial scales are the laser sheet thickness, which is delta Z naught, that is the thickness of the PIV plane of illumination, and delta is the PIV interrogation window. Eta is the Kolmogorov scale, and lambda is the Taylor microscale, and L is the integral scale. Now here you see that the PIV interrogation window is at least 4 times larger than the Kolmogorov scale. So what it means is that inside each PIV window, the flow can change significantly because you can fit in one large vortex as small as 4 Kolmogorov scales. So within each PIV window, your flow field can change a lot. But since PIV can produce only one velocity vector per interrogation box, so you, in some sense, you are losing, you're only computing some kind of average velocity field, and you're losing most of the structure within that PIV interrogation window. Further, if you look at delta Z naught, which is the laser sheet thickness, it is at least 2 orders of magnitude greater than the Kolmogorov scale. So it means that within that laser sheet, the flow is not uniform in the Z direction. You can have a very highly three-dimensional flow with eddies of varying sizes within the PIV slab. To show this, you can see this from this movie, which shows the particles within the 3D structure of the particles within the PIV slab. You can see that particles are not uniformly distributed in the Z direction or the normal to the PIV plane. There's a three-dimensional structure to it. And now when you convert this, when you try to capture this using PIV technique, which is inherently two-dimensional, you're bound to get errors. So these two, the sources of the error sources, the error sources 3 and 4 are in some sense inherent to the PIV technique for these high-speed flows. So in conclusion, we've performed first systematic numerical study to quantify the accuracy of PIV in homogeneous isotropic turbulent flows. We observed there's a noticeable gas phase turbulence modification due to particles. We also observed irregular sampling of the flow field by particles. Massless particles seem to show ideal behavior. We observed that the trajectory error is within a PIV window size for imaging frequency of 500 kilohertz. And comparison of the synthetic PIV reconstructed field shows the velocity statistics are more or less well captured, but the velocity gradient statistics are poorly reconstructed. And we also identify what are the possible sources of error in case of PIV. So the conclusion here is going to smaller particle size for PIV in homogeneous isotropic turbulence might be useful, but you still may be limited by the PIV resolution in these high intensity turbulent flows. Now, before I conclude, I'll spend a couple of minutes discussing some of the work that we have been doing on detonations in narrow channels using multi-step chemical kinetics. So this work is done in collaboration with Patrick Meager and Xin Yu from University of Connecticut, and Shan Jackson and Hai from University of Stanford. So as a part of this study, the first mixture that we looked at is hydrogen-oxygen argon mixture. It's what we call as a stable benign mixture at 0.2 atmospheres at 300 Kelvin. So the expected particle size here is 1.25 centimeters. So we carried out 2D simulations to see what is the effect of the channel width on the cell size. So we went from a wide channel of 4 centimeters all the way to 0.1 centimeters. So what you observe as you go from bottom to top is that in case of 4 centimeter wide channel, you have 4 cells. So the channel width is something like 1 centimeter. In 2 centimeter channel, you have 2 cells. Again, channel size, the cell width is 1 centimeter. But when you come to 1 centimeter channel, the cells seem to split, and you have 2 cells here as well. Here, the cell size is 0.5 centimeters. And when you go to like 0.5 centimeter domain, you have 1 cell, which indicates the cell size of 0.5. And as you go to 0.2, then you again have like this single-headed spinning detonation. And as you go further down, like 1 to very, very narrow channel, like 1 millimeter, we see no cells. There is no transverse motion to produce any cells, but we see a propagation of a detonation. Here, the detonation is quasi 1D, and it propagates with ZND solution. I have to mention that all these cases are with adiabatic slip walls, so there is no loss, no losses here. So these results raise 3 questions. So the first question is for a given chemical mixture at a given condition, is there a unique cell size, or the mixture can have multiple cells or cell multiplicity depending on the channel width? That's question number 1. And if so, what determines how many cells I'm going to have in a given channel? Is it the channel size, or is it the initial conditions, or what determines it? And thirdly, we observe that there is no minimum channel width. At least this mixture seems to propagate even in a very, very thin channel, as long as there are no losses. So do some mixtures have what is known as a critical radius or critical diameter, channel diameter, or some mixtures don't have. So these are some of the questions that we're looking at. We also looked at hydrogen-oxygen detonations at 15 kilopascals and 298 Kelvin. These are 3D detonations. And here we are looking what is the effect of channel width and the wall boundary conditions. So from the left, so here I'm showing some of the suit foils from our simulations. So as you go from top to bottom, you're increasing the channel width in 3D. Here the channel height is like 2 centimeters. We tried adiabatic slip, adiabatic no slip fall, and isothermal no slip fall. In case of adiabatic slip, you see that for the very, very narrow channel in 3D, there is very little deficit in velocity, and there is the transverse motion or the 3D behavior takes a while for it to onset, because in the third direction, there is not enough room for the third mode to get activated. But as you increase the channel width, you see that the third dimension motion of the detonation comes into play, and you see these streaks along the suit foil. Now, if you go to the adiabatic no slip case, so the wall is still adiabatic, so there is no heat loss at the wall, but you have a boundary layer, it is no slip. So we begin to see a velocity deficit, which comes from due to the momentum losses at the wall. So for the very narrow channel, you see a 10% deficit. There's no 3D behavior. There is no third dimension motion. But as you increase the channel width, the deficit seems to decrease, and the 3D behavior is present. Now, if you go to the isothermal no slip case, for the very, very narrow channel case, we saw a detonation failure due to significant velocity deficit. And as we increase, we also saw a failure at 2 millimeter wide channel. But as we increase the width of the domain, we see that the detonation propagates, but with noticeable deficit in velocity. Now, recently, we also started looking at 2D detonations in ethylene air mixtures at 1 bar and 298 Kelvin. So here I'm showing the suit foils for ethylene air at different channel widths and equivalence ratios. So we observe that as you go from, so if you consider phi equal to 1, it seems to propagate even in a narrow channel of 1 centimeter, a wide channel of 8 centimeters. The cells are irregular, but it seems to propagate. And here the cells are way off than what they should be. The cells should be roughly around 2 centimeters for the stoichiometric mixture. But here we see a hierarchy of cells. But as you get lean, we observed for the phi equal to 0.7, we observed failure in a 1 centimeter narrow channel and also at 8 centimeters. But we see that the detonation propagates with highly irregular cells for a 16 centimeter wide channel. So this indicates that there is some kind of critical channel width somewhere between 8 and 16 centimeters for the phi equal to 0.7. For 0.6 and 0.5, so far we see failure in both the narrow channels as well as wide channels up to 16 centimeters. So this is still work in progress. We're also looking at what causes these failures in lossless channels. We're also looking at also planning to see Lagrangian trajectories into these simulations to see if we can learn something from the Lagrangian thermochemical trajectories to see what triggers this failure even in a lossless channel. And with that, I think I'll conclude and take any questions. Thank you very much.
Thank you very much, Sandeep. We've got a couple questions from the chat.
Okay.
The first one is by Kareem Ahmed. I was wondering, Kareem, do you want to speak?
Sure, of course. Hello, Sandeep. How are you doing?
Hi, Kareem. I'm good. How are you?
Doing good. So I was just asking regarding the liquid jet breakup that you were showing. Are you modeling primary breakup, and can you talk a little bit more about it?
So here our particles are larger than the Kolmogorov scale.
Mhm.
So we don't do primary breakup. We do secondary atomization.
Okay. Okay.
And we just do secondary atomization since our droplets are larger than Kolmogorov scale. So all that turbulence does is move around the particles rather than affect the primary breakup.
Okay. All right. Very good.
Thank you. We've got another question from Myron Menezes. If you want to ask your question yourself, or I can read it.
Yeah, sure. So in slide 40, looking at your soot foils, the cell structures were very regular. And I was just wondering if this was done at a low activation energy, or what seems to be going on there?
Yes. Okay. So you're talking about hydrogen, oxygen, argon mixture?
Yep.
So hydrogen. So it's a by now it's a well-established fact that this is done using multi-step kinetics. So this is not single step. So and it's secondly, it's a well-established fact that argon dilution helps regularize the cells. So hydrogen, oxygen, argon is known to have regular cells. There's no irregularity in cells for hydrogen, oxygen, argon mixture.
Okay, thank you.
Okay, and we have 2 questions from Matej Radlescu.
Hi, thank you for your talk. I have 2 questions. First of all, in the first part of your talk of the particle role on detonations, I'm a bit surprised to learn that the particles have no effect on your detonation structure. So my question is, can you expand on how you couple the particles with the flow, and whether the particles are coupled both thermally and mechanically?
Yeah. So this is an interesting question that you raised. So our particles are aluminum oxide particles. So they are chemically inert, so they don't combust, but they are thermally active. So they exchange heat and momentum with the gas. So our solver is two-way coupled. Like the gas can give velocity and take velocity from the particles, as well as it can exchange energy, both thermal and kinetic energy with the particles. So we have the two-way coupling. Now, coming to your question that the particles didn't affect the detonation. So the seeding here, the seeding density plays a role. So the seeding density that we tried here is, if I'm not mistaken, is somewhere. Let me just go there. Okay. Yeah, the seeding density is like 2.5 trillion particles per meter cube. So this seeding density is typically what they use in experiments. We believe that there will be a seeding density after which your particles will start to affect the flow field, because particles can take heat from the flow field. So as you know, the detonation propagates because there is a heat release. The heat release gets coupled to the detonation front, which makes it propagate. So if you have enough number of particles that can take away significant amount of the heat release behind the shock, it is possible that they start to affect the thermodynamic state of the detonation. But at least for the seeding densities, that the density that we tried here, we didn't see the particles affecting the flow field. Does that answer your question?
Yeah, my second question is if you can comment on the relaxation time, both thermally and mechanically, of these particles in the flow as compared to some characteristic time or length scale of your detonation. Does the particle relax to the mean flow an order of magnitude faster than the induction time, an order of magnitude longer?
That's a really very good question. I don't have the data here, but we have it in our paper. So what we saw is the particle relaxation time is like sub-micron here, at least in the detonation case. And so what do you want to compare with here?
Let's say the induction time behind the shock.
The induction time, I don't exactly recollect what is the induction time behind the shock. But yeah, that will be an interesting thing to look at. Yeah.
If you have like the length that it takes to
the induction length, we can roughly, I think it's around, if it's 40 cells, I think it's around 316 micron, if I'm not wrong. I don't remember it on top of my head. I'm just estimating from the resolution that we used in the study. And
I think it's important to think about that if you want to explain why the particles don't extract or extract energy from the flow, or what's their role on your detonation.
Yeah.
Yeah. My second question it's in regards. It's more of a comment than a question. It's on the detonations in the narrow channel in the last part of your talk.
Yeah.
Now we've all done these calculations of detonations in narrow channels with no losses, but they're not quite physical in that by reducing the channel size to a very small dimension as to eliminate the cells, it's not something that you would be able to do in any sort of an experiment. It's a somewhat of an artificial numerical experiment.
Yeah,
but
it's please continue. Yeah.
But the observation that in some cases you go to a stable quasi 1D propagation, while in the other case it fails, it has to do with the stability of the 1D wave, in that very unstable ones are gonna dynamically quench for very long periods. And this has been documented in a physics of fluids paper by Lee and I can't remember. You can dig it up, I'm sure.
Okay. I agree with your first part of the comment that there might not be a practical system where you could do these very, very narrow channels experimentally and still see this quasi 1D propagation, because as you get narrow, you get losses. And this was more of an our numerical experiment too, because numerically you can do this, right? So that's what we did. We just kept reducing the channel width to see what happens. Do you eventually get like a 1D quasi a detonation, or do you fail? It's more of a numerical experiment.
Okay, thank you.
Mm-hmm.
Yeah, thank you. Are there any other questions?
I have two like short questions. The first one is like a continuing question from Professor Lascu's first question. It's about the way you model the coupling between the particle and the gas. So you basically you definitely consider there is a certain size of the particle in terms to compute the area for convective heat transfer and also the drag force, but is the volume of the particles are actually considered, or they are just like volumeless point sources?
These I should have clarified this. This is the particles are point particles. So we use their size to compute what will be the drag. So and what will be the heat transfer rate, but we are not modeling the particles. Sorry, we are not actually resolving the particles in some sense. They are just modeled.
Okay. So have you estimated what would be the for the seeding density you are considering here? What would be the volume fraction of the particles compared to the total?
It's less than 10 to the power minus 3. We keep track of what is the volume ratio, because our physics breaks down if the volume ratio, I mean the physics of the model of the particles start to break down as the volume fraction increases. So we constantly, the core constantly checks locally within each cell if the volume fraction is larger, and we have a warning that says, okay, the volume fraction is becoming larger.
Okay, I see. Yeah, it's good to know. And also my other question is about the sources of error. You commented on this source of error about the PIV concept or the PIV technology itself.
Yeah.
What about on the numerical side? Like, I believe like you guys must have already solved a lot of problems of tracking the particles, like how you
Yes.
consider what is the local gas properties or the flow parameters of the gas that need to be used to compute the local force and the heat transfer to the particle, right? I believe
Yes.
there would be some, I don't know, like interpolation or
Yeah.
is
So
there any like something we need to be careful about with that?
Yes, that's a very good question. I didn't speak much about this. So we have a JCP paper. The paper title is here. It's interpolation for Lagrangian particles in highly compressible flows. So this paper talks in depth about that how you should track a Lagrangian particle in highly compressible flows, both reacting and non-reacting, and how you must be careful when you do this.
Okay.
So you can just look up this paper.
Sure.
It's got accepted in 2019. So you can look up this paper.
Okay. Okay. Thank you. Thank you. Good to know. Thank you. Very interesting talk. Thanks.
Thank you.
Thanks. Are there any other questions? Sandeep, I'd like to thank you very much for your talk. I think the clustering that you show is, visually very beautiful. I was wondering what causes the particles to cluster, or where do they cluster along in a detonative flow?
So they begin to cluster downstream of the detonation. So if you ask me why they cluster, is because you have all these eddies. So eddy is basically a high pressure region and low pressure region, right? Moving in a circular motion. So they tend to push off these denser particles away from the center. So if you have two eddies beside one another, they tend to push the particles away from each other to a common region, and that's what creates a cluster. So this is an entire field of particle-laden turbulent flows, where people look at all these clustering and voids and see what causes them. So I can send you references to those papers to just look.
Okay. Yeah, thanks. I was kind of interested in knowing if the clustering happens, within the induction length or near the reaction zone of the detonation, or if it happens, very far downstream.
At least from our movies, visually, I don't know quantitatively, it seems to happen just right off the. So when you have like a triple point and you have an explosion, right? You have a jet, basically, and at the ends of the jet you have this shear. You have this shear which causes this mixing vortices to come up. So when you have these vortices, I think it starts to cause the particles to cluster. So at least visually, I can say it's right after the detonation crossing, well within the induction length, I would say. But I need to take a closer look at the data to quantify how bad is it within that region, how bad is it further downstream.
Okay, thanks. Yeah, I think, I personally would be very interested to know more about, how the scales of heat transfer from the gas to the particles, or vice versa, the momentum transfer, and this clustering happens compared to the length scales of the detonation themselves.
Okay.
So thank you very much for your presentation. I found it very
Thank
interesting. Unless there's any other questions, this will be the last call. Or any comments? I'd like to thank you one last time, Sandeep. Thank you very much for your talk. Thank you everyone for participating. Xiao Cheng, you have something?
No, it's fine for me. I would like to thank Sandeep again and thank everyone for attending the webinar today.